in Adapt Builder. And the version of Builder that we're using today, just for reference in case anyone's using older versions, this is the latest commercial release, Builder 2016.4. So if you're wondering where you can gather that information on your side, if you go to Help, About Builder, that will show us the current build that you're using on your machine. So if there are any questions today, please feel free to use the question panel on the GoToWebinar panel box that you should see on your end. There's an option there for questions, and I'll try my best to keep up with questions and to answer them. If there are questions that might be answered better using some of our more in-depth technical literature like technical notes or documentation, I may defer to that and send that to the question asker after the webinar. Also, if there are any questions related to specific issues that you might be having on your end, for example, crashing or troubleshooting type of questions related to a specific model that you might be working on, I would just ask if we can reserve those to some communication offline in the form of either a phone call or email. So you can always send questions to support@adaptsoft.com. So we'll go ahead and get started with our webinar. First, we're going to kind of just describe the geometry, give a model description of what it is we're working with. And many of you may have used the software for post-tensioned slabs and design, which is what historically Adapt is known for. I think is more PT design for slabs and beams. However, if you're familiar with the program with Builder or even with PTRC, Builder can be a very useful tool for evaluation and design of RC slabs, just conventionally reinforced two-way slabs with or without beams. And this example has a little bit more complexity in the fact that we have several beams that are included as part of the geometry. So if we look at our slab here, we have the main slab, which I've selected, is about 10.5 inches, and today we'll be working in US units and ACI code. So this main slab is 10.5 inches, and just for reference purposes, the location of the slab is at the reference plane number 3. So we've modeled this at reference plane 3. If I show a side view of the structure, you can see level 2 is the bottommost plane in this particular model. Level 3 is the current plane that the slabs and the columns and the beams, all of the components are referenced from level 3, and level 4 is the top plane. So today we'll be working in what we call single level mode as compared to global mode, which allows us to model a full multi-story frame in the software. We'll be working mainly in single level mode, and the way we tell which mode we're working in terms of analysis is from the Story Manager toolbar. There's an option here to toggle between single level mode and also full structure. We also call this global mode or multi-story mode, multi-level mode. Those all essentially mean the same thing. So if I toggle to full structure mode, you can see in this model nothing changes in terms of what you're viewing. It's the same model because, again, we've only modeled a slab, beams, columns, and walls above and below. However, the results would actually be different because depending on what mode you're working in, the program sets support conditions that are dependent on whether you're in single level or in multi-level mode. And if I go up to criteria, and in criteria under the analysis and design options tab, you can see that kind of towards the middle here, the support condition at far ends of walls and columns. For single level mode, this is by default set to a fixed roller condition. So it's rotationally fixed in XYZ, and it's released in the X and the Y for translation. If you use this and select multi-level, the multi-level condition is fixed. So because the two different modes of operability in the program have different assignments in terms of the support conditions, you would likely get different response in results, for example, in column moments or wall moments and shears and whatnot. So just be mindful of what mode you're running a model in, just from a general analysis perspective. And we'll come back to some of these analysis and design options as they pertain to the design of the design strips, and also as they pertain to RC slabs as compared to post-tension slab. Now this model has a little bit of complexity in that I have two slab steps, and let me go to a plan view. I'll turn on the wireframe view of the structure. We have the 10.5-inch slab, which earlier it's referenced from the level 3 with a 0-inch offset. We also have a slab which is 9 inches, and it has a 6-inch offset from level 3. So it's offset downward by 6 inches. This input is positive is downward, negative is upward from the reference plane. And then finally there's a third slab here which is 7.5 inches, and that is a 7.5-inch offset. The beams themselves are actually stepped such that the top of the beam follows the top of the slab and the bottom of the beam is flush along this entire path. So for example, this beam is 14 by 18.5 inches. This is set to the reference plane. There is not an offset. In other words, we don't offset it to the soffit of the slab. And whether you do that or not, there's not a huge difference in the results. There can be when you have upturned beams and when you have steps, depending on where it's offset. But in this case, it's not a significant difference. You can see the location here is 0 inches. The beam in the first offset is 14 by 16, and it has a 1.5-inch offset. And then the third beam is 14 by 15.5. So we're just essentially reducing the depth and the location such that this beam is completely flush. If we wanted to validate that, I can take a section cut through that frame line and insert it out here on the end, and we can see this is where the beam starts to step. So there's a step right there beyond the column face, and then there's a third step here, or a second step right here. So this allows us to do some more complex input of geometry in terms of beam modeling. Now the beams are segmented. In order to create different size of beams, we have to segment the beam. This beam and this beam are both segmented. And that's important to pay attention to when beams are segmented versus when they're not segmented, in terms of how the program considers the beam as part of a design section. And I'll talk more about that when we start setting up our support lines. So we have beams. The beams can have releases. If we double click on any beam, or even column or wall, vertical components can also be assigned releases. But we can see for our beams in this model, releases between beams and other components, nothing is released in terms of translation or rotation. Those are all left alone. Notice also that, going back to that input, if we go to stiffness modifiers, by default what we call a usage case, which is just a set of stiffness modifiers that the program uses when we analyze a frame or a structure. In this case, the default stiffness modifier is uncracked. Nothing has been reduced in terms of stiffness. Walls, columns, slabs are all set to 1. If we were to add a stiffness usage case, here I can just select, for example, edit usage, and I'll just select something here. We'll say slab stiffness. This is the name of the new usage case. And so once that's been defined, I can then select, for example, my slab regions, and we can either do this one by one. If I double click on a slab region, I can select stiffness modifiers and go in and assign the different modifiers for rotation or translation depending on the direction of the local axes. Or I can do this as a group. So if I, for example, either hand select the different slabs by pressing Control, or select by type, for example, slab region, that selects all of my slabs. Anytime I make a change to more than one component at the same time, we're going to use Modify Item Properties, and under the slab region tab, I can modify the stiffness for the new usage case that I've defined for slab stiffness. So let's say, this might be 0.5, for example. Actually, for RC slab, it might be less, but we'll just say 0.5 arbitrarily. And once we've assigned a usage case, we'll say OK. And then if I go back just to check that usage under the slab that's selected, we can see that modifier set has been included here. So when I analyze the structure, let me go back to, I'm going to run everything today in single level mode, by the way. I need to go back to single level. When I analyze this model, and I'll go ahead and mesh the slab first. When I analyze this under FEM and Analyze, you're going to see that there's an option here to apply stiffness modifiers. So by default, the modifier set is uncracked. If you wanted to apply that usage case that I just defined for my slabs, I could select slab stiffness and run the analysis relative to that usage case versus just the default uncracked case. So that just gives an example of how you can assign modifiers to your components. Now, one thing that's very important to note is that when we check the slab for cracking, and in this model we've set up combinations that I'll discuss a little more in detail later on in the presentation. When we check the slab for cracking, the basis for which the program determines whether or not the slab or the beams have cracked under a given set of loads for a given crack deflection combination, for example, self-weight only, the basis that the program checks against is the uncracked state. So many times users might set up a modification usage case where they've already established a reduction in the slab stiffness for bending. And when they go ahead and run the crack deflection, the result can actually come out such that the uncracked, or let's say the general frame analysis reports a higher deflection than the cracked analysis. And that's because your general frame analysis, if I run this, for example, using slab stiffness, this is what I'm referring to as the general frame analysis under some condition using this usage case, this could result in higher deflection because I've artificially cracked the slab by means of a stiffness modifier. And this could result in a higher deflection than the actual cracked condition, which is using the uncracked state as the basis for which the program determines whether or not the slab has cracked. So in short, whenever you're checking crack deflections in the software, you need to make sure that you run the model with the uncracked stiffness case versus some predefined usage case here. Okay, so we'll run things today in uncracked, in the default uncracked state. Loading on the structure is pretty simple. I didn't go ahead and add a bunch of complicated loading. There's no lateral load. We're looking today really at just gravity, being in the fact that we're in single level mode. We could add lateral load if we were running this in multi-story mode, and we could reapply reactions to this slab from the global analysis, but today we're keeping it fairly simple in how we're obtaining the results. Loading in this case, if I turn on from select set view items, the loads, we have no point loads, no line loads, we only have uniform or patch loading. And here we have dead load. The dead load magnitude is 20 pounds per square foot. You'll note that the dead load here actually extends out beyond the slab. That's okay. When the program runs the analysis, only loads that are actually discretized to shell nodes are going to be used. You can see right here, there's an area right there that does not include any loading. So here I might want to make a modification. What happened was I assigned and mapped my loading to a slab, and then the slab was changed. So if I wanted to configure the load area, I can do that. I can add points, I can delete points that are positioned on the load map. And so what I can do here, if I move this point to this location, well, now I have this little triangular region where I have some overlap out into space where there's no slab. If I use the option for inserting a point and I insert a point there, it adds a point here. If I add that point again, it adds a point there. So it's almost a guessing game. It actually depends on the sequence of nodes that are assigned to the slab. So a lot of times if it inserts it on the wrong span, you just insert another versus going and determining what the numbers are for those points. But anyway, you can move that point now to the corner if you want to have a perfectly aligned loading arrangement relative to the slab. So it's not required, but you can do that if you need to. The live load on the structure is as follows. I have actually 2 live loads assigned. The first live load, if we double click on this, is 50 pounds per square foot. And you can see that live load actually wraps around the entire perimeter of the slab. The second live load that I have on the structure, which is shown here, is also 50 pounds per square foot. And that is only assigned in a specific portion of the slab, not the entire thing. The loading on the slab is always additive in the program. It never displaces the previous load. So in this case, in this region, and I'll use my highlighter to outline this, in the region shown here, this is 100 pounds per square foot because I get the 50 plus the 50 that's assigned here. If I would have made this input negative 50, which you can do, you can input a negative load, the loading here would have been 0. So there are ways to play with loads to try to reduce load or increase load depending on the overlap. One other way is just if this is 50 and this is 100, I could have assigned load only in this zone, which would have been maybe 50, and then I could have directly applied 100 in this zone. So there's multiple ways to add the loading. Okay, so that's the load. In terms of the combinations, when we define a model under criteria and design code, in this case we're using ACI 2011, whether we use ACI or Canadian code or European, Indian code, whatever we select, the program will predefine specific combinations. So under loading, load combinations, tabular input, the program will have 4 or 5 combinations typically, which are really only relative to gravity service and gravity strength or factored level forces. And the user has the ability then to add as many additional load combinations as he or she wants in terms of what the program will process. So if you apply lateral loads, those will also be applicable in this box. You'll see the lateral load case shown at the top, and you can assign factors to that load case. There's a question. Let me go ahead and answer that. Why is the default shear modified to 0.85? Are you talking about the reduction factor in the criteria? So let me just turn this off for a moment. Okay, so the question is, let me go back to criteria. If we go to criteria, under the shear, this criteria is set to beam, and these reduction factors are specific to whatever criteria we have set here. So for a 2-way slab, it's 0.85, 1-way slab, 0.85, beam, 0.85. It could have just simply been a programming error, to be honest, where this was never updated. If I toggle to a different load case, those would reflect what the default should be out of that design code. But as a user, you can always modify this and store that as a default from file, save as default values. So if you needed to change it, you have the ability to change it. It might be 0.75. I can't remember what the code value is for ACI, but it could be 0.75. All right. You're welcome. Thanks, Morgan, for the question. Going back into the loading menu, I'll explain now how the program handles these load, the analysis and design options for the load combinations. There's different tags, I'll call them, that you can apply to any combination. Service sustained and service total. Those apply, I think, historically, those might be more in tune with, let's say, a post-tension design when we're checking stresses or deflections for a slab. So in terms of reinforcement, the program, when we have a combination set to service total or service sustained for an RC slab, the reinforcement output for either of these two load combinations would actually be identical. For a post-tension slab, that's not necessarily true because you have different stress levels for both combinations because we have less live load in one of them, and some of the quote-unquote service or minimum rebar for PT is dependent on the stress level. But in terms of the RC condition, this for ACI rather, I'm not an expert on all other design codes, but for example, for ACI, we would get identical minimum rebar or service rebar from these two load combinations. So the program, when it solves reinforcement for service total or sustained, it looks at the code that's been selected, what the minimum requirements are, for example, for a two-way slab or for a beam, and it applies that to this load combination. So for beam minimum rebar, we might get minimum flexural steel, and for a two-way slab, we would get minimum temperature shrinkage steel that the program calculates. For any combination that is set to strength, we have two strength combinations in this example. The program designs reinforcement necessary to meet the factored demand moments at every design cut for these combinations. So it evaluates all strength combinations and adds reinforcement necessary to meet the demand moments for those combinations. There is one condition where the program does not meet strength requirements, and it's a condition that is actually not in this version. It happens in version 2015 and also 2016.0 through 2016.2, I believe. And when you have a design cut which extends over a wall, let's say we have a strip, and this is the path of the design strip, and we have design cuts along this strip which are cut perpendicular to this strip. Any design cut that extends over a wall, or it could be partially into a wall. For example, if I have a design cut here which extends over this wall, the program only calculates the minimum service reinforcement for that design cut versus the strength rebar. So if we have two cuts on either end of a wall, many times we're going to have a demand moment which might be a negative peak, and then it drops down, and then a peak, and then something like this. It looks like Batman here. So at this moment, this is a negative moment and a negative moment. That moment could technically be just outside of the wall, but the moment or the section cut just to the right of that, which is inside of the wall, might have a demand there of, let's say, negative 100 kip feet. The program does not design for this section cut here, but it does design for the cut outside of the wall. So as a user, when you're investigating results, you might see a pink design cut that's flagged at sections cut into walls, and that's because the demand moment is for strength is technically, it could be greater than what the capacity is there from the service or minimum reinforcement that's being provided at that section. And it's alarming to users In the current version of the software, whenever you have a design cut extend over a wall, let me just erase that. If we have a design cut over the wall in the current version, the program just simply doesn't provide any result for these cuts over a wall. And you say, well, how do I get results then near the wall? Okay, so that could be a problem. You might want results on either side of the wall, maybe not directly over the wall because there's no bending happening at that immediate spot. So we can do things with the design strips that allow us to do that. And one thing that we can do is if we have, let me go ahead and just zoom in here. If we have a support line along this path, so we have a node here and a node there. This is a little bit sloppy, but I'm trying to draw a straight line there. We have a support line that extends over the wall, and we might actually add a support line just to the side of this main support line. And by doing that, we might have splitters that cut up to the next support line, below to the next support line. But what happens in this case is the tributary region over the actual wall becomes very small, it's basically this. This is the tributary region over the wall. The program doesn't design for sections in that tributary, but it does design for sections related to this strip and this strip, which might have design cuts that look like this and look like this. And I'll show you an example of this when we set up our strips, but this would allow you to get reinforcement near the wall but not directly over the wall. So there are certain ways to set up design strips in a more complex way or manner to obtain those types of results. Okay. Let's go ahead and transition over to, actually let me go back quickly to the combinations. We need to finish that discussion. The other combination types that I've defined in this example are crack deflection. Whenever you tag a combination for crack deflection, the program calculates and it checks that loading condition for whether or not the slab has cracked. So the program will produce two results. It will give you the uncracked elastic state or deflection of the slab, and it will also give you the cracked deflection of the slab if it's cracked. If it hasn't cracked under that loading state, then in essence the contours are identical and you basically don't get a result. If it has cracked, you're going to see that the deflections change, and we can actually review the cracking regions in the slab, cracking or let's say loss of stiffness about both orthogonal directions. So in this example, we've created three combinations to check for cracking, and it's somewhat of a stage-wise approach. So we've checked for self-weight, so we set self-weight to cracked. We set self-weight in the superimposed dead load also to cracked, and then we have the third stage, which is adding in the live load. And then what we do is we extract the deflection for each of the unique combinations. So we already have a direct result for self-weight. That's self-weight only. We know what that crack deflection is if it does crack, but we don't really know what superimposed dead load is. So we take SDL only. We're just simply taking stage 2, which is self-weight plus super dead, and we're subtracting out self-weight only. And then we do the same thing for live load. We're taking stage 3 and subtracting out stage 2 to extract the live load deflection. And then we reassemble those individual deflections into our total long-term deflection, for example. And this can be done many different ways. I mean, you have the ability to manipulate these load combinations and the factors however you wish. But in this is obviously an example here. For long-term deflection, we're manually applying the creep factor to this deflection. So we take 3 times self-weight only. We're assuming self-weight is a sustained condition, and our creep factor is 2. That's the assumption in this factor of 3, let's say. We assume that superimposed dead load is also a sustained load. Therefore, we get sustained plus creep times sustained, which equals the 3. And for live load, we're saying that only a portion of the live load is sustained, so we have a smaller factor here for the live load in terms of the long-term deflection. But the long-term deflection tag that you see here is really just a means to combine the results of other combinations together as a product of the or as a result of the actual combination that's being defined. So SDL only set to long term just allows me to take one minus the other or one plus the other, whatever the result needs to be. All right, we're going to go ahead now and look at support lines. So one of the fundamental, I guess, fundamental functions in the program is the ability to generate design strips. And this is something that's in other programs also. Design strips can be really, it's flexible enough to where as a user you can input these different ways. For example, we're going to define design strips in the X direction and the Y direction. So as a user, I could go in and say, okay, I'm going to set up one design strip. I'll just create a support line. It's actually the strip is generated from our input of support lines. So we first needed model support lines, which the program uses to generate the design strips. So I'll input a support line. When I start drawing the support line, I need to know which direction I'm drawing in, because if I'm drawing in the Y direction and then I overlap with another Y direction, I'll get an error. And there's a question. Let me just pause here for a question. Yeah, question is, can I explain a little bit about load patterns? Yes, sure. Let me do that. So I'll put the support lines on pause. Load patterning in the program requires input of what we call subregions. So when I input, let's say I go back to loading, skip patterns, and I create subregions. Subregions can be created as closed polygons, or I can input, let's say, almost they're like grid lines that allow the program to determine the subregions. So I'll first do the grid line method, where I'm just simply going to put in a line from side to side, and I'll try to just follow the frame directions, for example. And then I'll do the other direction here. So there's might be a line here, and then one here. Okay, so that defines my subregions. And when I go back to loading, skip pattern, define and edit the load patterns, you can see that the program takes those lines that are bisecting one another and it generates the actual pattern or the region. So for example, this is one region, this is another region that's bisected by the X and Y lines. This right here is another region, and so on. And the regions are all defined by this little handle. If I select that handle, that shows me what the subregion is. So for every subregion, I can choose whether or not for the program to reduce the live load. And for example, the load case that I want to be able to reduce, there are two default load cases here. There's dead and live. I'll just assume live is what I'm going to reduce. So I'll reduce the load. I can also apply a skip factor, which means that any region that's turned on for that particular pattern that's defined will be multiplied by this skip factor. So if the live load is 100, the skip factor is 0.7, you'll get 70 PSF, for example, applied in that particular region. So now we define the patterns. So probably the easiest way to do this, rather than sit here and try to press control and hold these, select those buttons, I'm just going to turn off everything except for their subregions. So I just display only the subregions, and that can also be done in the blue eyeglasses. If we go to skip loading, that turns the subregions on and off. And now what I can do is just window select. So the first pattern will be everything. I'll say I want to add pattern 1. That means every region is loaded. However, every region will also be reduced in terms of live load. So this result would actually be different than if you ran a combination 1 times live load versus 1 times pattern 1. You would get a different result. The second pattern might be, let's see, something like this. That's pattern 2. Third pattern, might be, actually I have one pattern that outlines everything, so I need to window, or excuse me, hand pick these. So this is pattern 3. And you can put several, you can put as many patterns as you need to into this dialog. Select OK. And once you create patterns, the program then lists those patterns in the load combination box. So within this box, you can individually include patterns as part of a load combination. You can include the enveloped max and min here as part of a combination, and the program would then evaluate the slab for the pattern loading. So that's one way to do that. There are other ways to introduce pattern loading, but it's more time consuming and difficult to do that. It's basically by manual input. Does that answer the question? Okay, I think so. All right, so let's go back to default display. What I'm going to do is actually delete those patterns out, and so I'll select by type my subregions and just delete those. We're back to square one in terms of the strips. So for design strips, as I mentioned earlier, this is pretty flexible with how these can be input. So I could take a strip, I can go to support line. Earlier I mentioned we're going to work on the X support line first, or the X direction first. I'll go to the properties and make sure this is set to X direction. So arbitrarily I could say it's Y direction, but then the actual global Y would become X, and it becomes confusing, obviously. But so we're going to keep the directions the same as the global orientation of the model. And here I could go in and let's say I just arbitrarily put in some support line, and I could then take that support line, I could modify, copy, move, and I'm going to copy this support line down every -5 feet, and I'll just put 30 in here and copy that, and now I have support lines every 5 feet. If I was to generate the design strips, and I could do the same for the Y direction. So if I generate my design sections now, under the strips menu, this is going to generate the tributary region and all of my design cuts in the slab. So under generate tributaries, the program generates the tributary regions, and I look at this and I say, okay, it looks a little bit strange because right now I'm seeing I'll mark this for us, I'm seeing the support line number 1, I'm seeing the colored tributary region number 2, and then I'm seeing these perpendicular design cuts number 3, which look very sparse in the model. There's not many design cuts. And so if I go back to blue eyeglasses, I'm going to boil this down to only showing the support line with the design cuts. And you can see that this just is not uniform enough. It seems almost random in where the program is taking the design cuts. And the reason it's doing this is because the program defines the number of design cuts based on the span. So the definition of design cut is 12 per span, but in this case the span is from point 1 way over here to point 2 over here. So what I can do is I can go ahead and just either manually for each support line go to my design section options and increase the number of sections per span. Maybe I'll make this 50. but that's time consuming. I don't want to do that for every support line. So I'll just select all of them, modify the properties of the support lines, and let's do 75. And then I'll regenerate my strips. And now I get more uniformity in the output of the strips. So now every 5 feet I have a strip. I'm having the program evaluate the design cuts that you see along each design strip, which is 5 feet wide. And again, you could produce this in both directions. So that's method one, where you can input this. One thing to watch out for in this particular method is the program's placement of minimum reinforcement. Surface reinforcement is dependent on the location of the span vertices. So this point and this point technically don't represent where you actually have a support along, for example, a column strip. So your minimum reinforcement almost gets thrown out of the window when you do this method. This is good if you're doing an evaluation of strength reinforcement, but not minimum reinforcement, which is why we recommend doing using the second method, which is what I'll show you now. So I'll leave this model just for a moment. I'm going to go over to another model which is identical to this, and this model is set up such that the support lines are actually placed over my frame lines. So I start the support line. This is an X direction support line. I start it at the end of the slab. I go to the center of the support, center of the next support, and so on. So I have just a few design strips in this direction and also along this beam here and the beam at the bottom. So it's along each frame line. And the same thing is true for my Y direction. If I turn on the Y direction, you can see I have this set along each frame line. If you double click on the support line, and I'll double click here on this one, we have to specify what the design criteria is for this support line. So for example, this support line, if I go to design, is set to a two-way slab. But the problem is I have beams along the support line right here and right there. And the entire support line is continuous, and it's set to two-way slab. The program has an option that's defaulted to in criteria under analysis and design options, which tell the designer, when we design the section cuts, design the beams using the code requirements for beams. So the program is smart enough to know that if there's a continuous support line set to two-way slab or even one-way slab, and there's beams that are included along the support line path, design the design cuts that intersect the beam, which would be here, 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 and then down here. Design these cuts for strength and service relative to design requirements for beams. The only downside to using a continuous support line like this is when the program creates the reinforcement output for this beam and this beam, the sizing of that reinforcement will be relative to a two-way slab. So if we go back over to this criteria menu and I look at the preferred reinforcement for two-way slabs, if this reinforcement is different than beam, the placement and the layout of the rebar would be related to two-way slabs, not to a beam. That doesn't mean that for example, I'll give you an example what I'm referring to. The bottom reinforcement for this area might show, you know, 2 number 5 bars bottom, but it might show the bars distributed like this. Okay, and you say, well, that's weird because the bottom should be at the bottom of a beam. The section really looks like this, and the user says, well, do these bottom bars go here or do they go down here? Okay, so whenever you have a design cut which intercepts a beam like this one, then the bottom bars are always to be placed at the lowest effective depth of the beam of the section, which is here, not here. The reason you get the distribution shown like this is because this is actually this is defined as a two-way slab, not a beam support line. So there are advantages to inputting the support lines this way, just in terms of speed and efficiency, but there's also disadvantages on the result side, where you just have to know what the program is doing, that may require you to go to a different option, which would be, instead of making this continuous, do a support line from here to here, which is a beam support line. Then this support line would be two-way slab, and then a third support line would be beam. And then because you have breaks in the support line here, that requires the use of a virtual boundary, which we call a splitter. But that would give you discrete rebar, for each unique design strip. Let me go ahead and erase that. Okay, so in this model, I've modeled my support lines, all of them as continuous. Now I'll mention one other thing. Whenever you have beams in a model, I would always recommend going to criteria, under analysis and design options, turn on the option for include waffle and joist construction. All that means is that the program, if the design cut goes through a beam, the beam is considered as part of the design section. And if the other option is used, regular floor system, what can happen is as follows. And let me give you an example. In this case, the beam and the support line node are at the same position. This support line point right there snaps on the beam end. So it triggers the program to include that beam as part of a design cut when we analyze when we design the sections. The same thing over here. The support line node is at that beam end. But let's say the support line node was actually up here and down here. Okay, from a design section standpoint, the design sections would look similar. You would get a design cut that goes through like so, and you think, okay, great, it's considering the beam, so the beam should look like this when it evaluates it. But in reality, because this point is not on that end of the beam, or this point is not on that end, or both, the actual section that the program designs for is a flat slab. It ignores the beam stem, and you get more rebar than what's expected because of that. So to bypass that, to always ensure that this happens, you use the waffle and joist construction. So it's just a simple way to ensure that it's using the right section. Okay, and I'll go ahead and just move that back to where it was. Now, in criteria, when we go to analysis and design options, there's an option here that says, do you want the program to create column strips and middle strips? In other words, do we want the program to automatically try and generate our middle strips? This works well if you have a square or a rectangle, but it doesn't work very well when you have lots of reentrant corners and there's a lot of jogging in and out on the perimeter of a slab. So we have this set to yes currently, and I'll show you what the result is for this set of design strips. The program is essentially going to try to create a middle strip between each column strip, which become uneditable. The user cannot edit these strips, so it's a little bit rigid in how it functions. So if I go ahead and I go to strips, generate the design sections automatically, and I can't really tell what the tributaries are in this view, but what I could do is go to reports, under graphical reports, design plans. I'm going to look at the design strips in the X direction, and this will show me just a tributary outline of my strips. So We have a middle strip here, or excuse me, a column strip there, a column strip in the green. Those are the strips that we defined, or the support lines we defined. This is column strip. This is a quote-unquote column strip. It's actually a beam, and then we have another strip down here. And the program has added middle strips. So it's added this middle strip here. I'll just signify this by an M. It added this middle strip, this one. It added this middle strip right here that you can see. I'll put a box around that. And it terminates at this location because the support line number 5, which dictates where it ends, stops here. So the middle strip also stops at the same position. And then it also added another middle strip right here. You say, well, that's weird. Why didn't this middle strip continue all the way over to here? And I'll show you that now. If we look at the way the support lines are laid out, let me just go to my default and go to X. So this support line at the bottom extends all the way over to the slab edge, and there's this extra span here. The support line above goes all the way over to this edge, and then there's another support line along this beam. So the program, because it adds this middle strip right here at the end point of this beam line, so there's this middle strip, but then it adds an additional middle strip between here and this beam because of this extension right here. So you get this strange little support line in the middle of the of this kind of slab at this depressed slab at the bottom. And so something like that you could probably live with, but you may not like that. You want to have more control over what the program is defining. So the only other option is for the user to manually define all of the strips, both column strip and middle strip. And that's the third model that I'll show you, is a model that has all of these defined in the same model. So in criteria of this model, you'll note that under the analysis and design options, I've turned off the column middle strip option, and I've input all of my column strips the same way I did in the previous model. These are actually identical to the previous model, but I've also included middle strips. And the program in this case is taking whatever this distance is taking half of that distance, like so, and this becomes the middle strip tributary. Now, if you want the ability to define how wide the strip becomes, then you have to include what we call splitters, which are these blue kind of little tick-marked lines. And I could add splitters to any location. For example, let me go ahead and clear the drawing again. If I generate my design strips for this example, and I'll just turn on the X direction, you're going to see that the program, by means of determining the distance to the next support line or the perimeter slab edge, the program dictates what the tributary becomes. So this tributary for this beam section actually becomes the distance between this point and this point. So there's a flange on top of that beam. And again, we have integrated beams included in the slab. So if I look at that, if I double click on that cut and I go to design sections, you can see that flange is 126 inches wide by 18 inches deep, and this is the physical design cut for that section. You say, well, I don't want to use that flange for the design of that beam. I want the beam to just be rectangular. So how do I tell the program, don't add a flange to this beam? So what you have to do in that case is the user has to add those boundaries, those splitters. So if I was to add splitters to this beam, I could go in and under strips create a splitter. This needs to be an X direction splitter because it's used for the X direction generation of strips. I could add a splitter, for example, along each face of this beam, like so. And once I do that and I regenerate my strips, where am I here? Regenerate tributaries. And again, I'll go to the X direction. The support line along the beam now includes just a tiny bit of slab on either side, and I could double click again on the strip. There's just a little bit of flange overhang, so we'll just say it's rectangular. But the support line below, this middle strip now extends all the way up to that splitter, because in the previous run there was no splitter, so the program knew to separate the two and divide it in half. Now the strip extends all the way up to the splitter, and because I have a splitter on the top side, there's no support line on the top side. This becomes void of any design cuts over in this region here. So I would have to add another support line along this edge. So to dictate the flange width of beams in the program and how the program evaluates those beams, the user has to use these boundaries or these splitters in order to dictate how wide the flange is. Otherwise, the program just uses the tributary related to the actual strip for the design of the beam. And I'll go ahead and discard that. I'm going to turn off those, or I'll delete out those splitters here. Okay, the last thing we'll show today, I'll go likely another 10 minutes, so I realize we're coming up on 2 o'clock. We were scheduled for an hour. I'm going to show just a little bit more in terms of a design process, and then we'll conclude, but let's go ahead and do that. First, we're going to mesh the structure. So we've set up all of our strips and support lines. We mesh the slab. And then the next step is to analyze the slab. So we're going to analyze the structure. And again, I have several combinations that I want to analyze. In order to run the crack deflection, we have to calculate the reinforcement first, because the crack deflection check is dependent on a calculation of the cracked moment of inertia for each of the design cuts. So in general, the more refined the mesh is, and the more design cuts you have, the more accuracy you're going to get in the crack deflection check. So in this example, what we have in place is good enough. It's sufficient for the crack deflection. But again, if you're looking to localize results with more accuracy, you can always adjust meshing and design strips. So we'll go ahead and analyze. We're going to analyze for uncracked. We discussed the stiffness modifiers earlier. And you'll see this box that appears on the left. This is simply a debug thing, and that's internal to my install. But so if you're worried that you don't see that on your side, that's okay. That's not included really in the commercial version that you have. Okay, we'll go ahead and save the analysis. And once we've saved the analysis, one thing that I'll note that some users have asked questions on this is, after I analyze, if I go up here to beams, where is it? It's in this branch setting. If I, for example, look at the moments for, under the actions for beams, so action diagram, moments about SS and about ZZ. So if we look at these diagrams, we see, well, we have moments in the beams. Remember, the program comprises the model of frame elements where there's a beam. So I could turn on the frame element view. If I go here to frame elements or shell elements, this beam right here is broken up into several frame elements with nodes on either end. So the beam itself has a moment diagram, but the slab also has moments at each of the shells. So once we generate the design sections and analyze them, then we get a secondary result, which is called the design section results. And the design section moment is essentially the composite moment that we calculate relative to both the slab and the beam being one combined monolithic piece of concrete. And it's those moments that we actually design reinforcement for. We do not design reinforcement for the individual component frame actions like these actions that you're seeing on screen. So these are just the frame element results that you're seeing currently. So once we take this one step further, I'll now go back to strips. I'll generate my design cuts, and I'm going to design the design sections. So now I'm going to process the evaluation of each of the design cuts along each strip for the composite or the combined result of both slab moments and beam moments wherever we have that actual condition. A large part of this model we only have slab, so we get the moments for just that one component, but where we have beams we have a combined set of actions that we're working with. Yeah, Charbel had asked if there's going to be a link for this session for anyone that has to leave early. The recording of this webinar will be placed on our YouTube channel, which is youtube.com/ADAPSupport. There's a playlist that says webinars, and all of our webinars will be loaded to that playlist if you need to review the recording afterwards. Okay, so the design cuts have been evaluated. Let me just clear the screen and reset. If I now look at the bending moments for design sections, you can see, for example, the bending moments now for these design cuts are reflective of the moment both for the slab and the beam, and it's these moments and shears or axial forces that the program is designing for. So for example, if I double click on this section cut under the design section tab, I have my physical geometry, which is shown in the top image. The idealized geometry, which is shown in the bottom view, is what the program is using to determine reinforcement for. And in this case, at this exact location, I need 3.5 square inches of reinforcement to meet the strength dead and live condition. This is the controlling condition which produces the greatest amount of reinforcement necessary for that particular design cut. And this is being evaluated as a beam, an RC beam section. We have capacity, demand, positive and negative values, demand capacity ratio shown, as well as shear capacity. This is the concrete capacity only, and a VU over FVC ratio shown here for the beam design. And notice that this is included on a continuous design strip. So if I, for example, was to go to another section cut over towards the end where there's no beam, the program, well, this is all specified as beam RC. Yeah, this support line, if I look at it, let me go to design, this is already specified as beam. So every section along this strip is being designed as a beam section. To generate the reinforcement, these, if I look at both directions, I can gather results for both directions. And I would recommend, if you're new to the software or getting used to the software, there's several other options that are more in depth that I just can't explain in the webinar here, but in the result display settings, there, you can look at any action. For post-tension slabs, you can look at stresses in terms of the support lines. One of the nice tools is the moment capacity with demand. So this shows me, for example, where I have positive and negative capacity. The blue is negative capacity, the green is positive capacity, and the gray is essentially the demand. And wherever you have the gray stacked right on top of the green positive diagram, that tells me that strength is controlling the section because I have zero reserve where service might be controlling. So where you have inflection points, like in this zone here, you have this gap between the demand and the positive capacity, and that's easy to tell because the demand capacity ratio is 0.15. So that tells me that at that section, minimum reinforcement controls. And if I go to the section, look at the design section, you can see service total controls the amount of reinforcement for that design cut. So there's a lot to be looked at in terms of these graphical results. Going down to that wall location where I have the design cuts over the wall, notice that there's no blue or green or gray diagram. It just shows the moment diagram. These section cuts are not being designed. So if I double click on that cut, under design section, you're going to see that the program graphically does not produce a result, but in this dialog, the program shows that it does calculate some minimum reinforcement, but no strength reinforcement. So if you ever wanted to investigate, well, I want to know what the minimum bars are over walls, you have to go into this dialog to see what that value is from a, I guess, a tabular standpoint or a textual standpoint. Graphically, to produce the reinforcement output under the FEM tab, generate reinforcement drawing, the user has the option to do multiple things. We can generate it for the global envelope, meaning all load combinations, service envelope, strength envelope only, or individual combinations. And this will produce an outline or a layout of the reinforcement in the slab. By default, the reinforcement is aligned with the direction of the support line, but the user has the ability to change that when we produce the result. For example, you can see this bar is kind of on a diagonal. It follows the direction of that support line, but I wanted to align everything orthogonally. So if we go back to the generate reinforcement, I can select the option to align with orthogonal axes, and you'll see that this bar gets converted in terms of the area of steel and also the placement. There's another question here. Is there any way to pin the beam at the end of the beam string? Yes, if we go to, like, let's say we have this string along this, there's 3 spans here. If I go to the first beam and I, under releases, I release the first side about rotation about SS, and I'm assuming that this is my start and this is my end point. If I model them backwards, then I would actually release this side. So, and then I would do the same thing on the opposite end of the string. So this would be released here. I think that answers the question. If not, just let me know. Note, however, that even though I release the beam bending, the section cut still has slab associated with it. So if you're expecting to see a zero moment at the end, you would see zero moment if you look at only the beam bending diagram, but because the design cut includes both beam and slab, you're still going to have some bending at that location, probably negative bending. What's the easiest way to clear the reinforcement that has been designed or generated? So I'll assume that you're talking about the program calculated reinforcement. If you want to clear it in terms of remove it from the model, that will happen automatically the next time you design the sections or generate the reinforcement or do that 2-step process. If you don't want to see it at all, for example, if I generate the rebar for envelope again, and let's say I want to get rid of it, I want to remove it from the view. Okay, so here's our rebar. If I use the rebar toolbar to turn the view of the rebar off or to isolate the rebar, I can go into the rebar display settings where I can turn off the view of specific X and Y top or bottom bars. Or I can just turn everything off by using this icon to display and hide the rebar. That turns it off or on. If I want to delete it, I would select by type rebar and then delete it. But next time I go back to FEM generate rebar, I end up with the same thing. So if you add user-defined rebar, in order for that rebar to not be considered in the next design section call, then you have to delete it like I just showed you. You have to isolate the base rebar and then delete it out of the model. Otherwise, it's always considered when you do the design of the sections. Yeah, Lawrence, the question is, I mentioned that I was going to describe the difference of modeling beam in segments and continuously. That was actually answered when I discussed how the well, it was a little bit vague. So I mentioned that when you set up your support lines, if you don't snap the point to the end of the beam, then you get a situation where the beam is not considered as part of the design cut. What happens is a lot of times, let me give you an example here. If you have a slab, actually let me launch a new instance of the program to show this. And I'll go ahead and build a slab. So let's say you have a diagonal side or edge on a model. And on this edge, we have columns like here, and then I'll add some columns over here, maybe one there and one there. And then I have a beam from here down to there, and I'll add 3 support lines. So we'll create a support line. Let me turn on snap perpendicular. People ask me, why not use the support line wizard? So I'll use that now. Support line wizard for X direction. If you use this, then you just click on 2 endpoints and it scans and adds a support line. Okay, so when I generate my strips in this type of a configuration where I have a diagonal edge, and let me turn off the middle strip option to show this more cleanly. I'll turn off middle strip. What happens is we're left with these gaps. Kind of here, there's a triangular gap, and this is more exaggerated when we have, for example, a support line that might be terminated at the column. But essentially what happens is we end up with these huge gaps in a model because the program looks for the end and the start point of a support, and beams that are perpendicular or within, I think, 30 degrees from the direction of the support line, those beams technically are supports for the design strip. And you end up with these big gaps in the slab that you want design sections in. So what we recommend is to fix that, what happens is the user has to segment the beam. So you end up taking this beam and you create multiple segments for this beam. So there's segment 1, segment 2, segment 3. In terms of like action continuity, this would produce the same moment diagram that you would get from the beam being one segment. But from a support line standpoint, when I go in and I generate my support line in the X or in the Y direction, if I go and click on that point, and I have that regular floor system selected in criteria under my analysis options, what's going to happen is the section cuts that are within this segment and this segment, those cuts will not include the beam stem because their endpoints are not clicked on. So that was my comment related to segmenting beams. and that can completely be bypassed if you use the option for waffle joist construction. So hopefully that clarifies. Another question was, when we have a beam and a slab, does the program double the area of stiffness for portions of the beam that is overlapping? Yes, it will. Not that that's a good thing, but it does double count. So if you have a slab, and this is our reference plane here, and you have a beam like so, this zone would be double counted for stiffness. So that's one reason why you might offset the beam such that it's at the bottom of the slab. Other questions? And I'll wait 2 or 3 minutes here to see if any other questions flow in, but that concludes today's webinar. Just a reminder, we will add the video to our YouTube channel, youtube.com/adaptsupport. And if you have any questions outside of the webinar, just feel free to contact us at support@adaptsoft.com. Again, I'll stick around for another 2 or 3 minutes or so to see if any questions come in, but I appreciate everyone joining today, and hopefully you've found it useful. So again, thank you. So there's a question, is there a way to design the beam as a T-beam, not a rectangular beam? Yes, if I go back to, let's see, I think it's this model here. Let me clear the screen. So if a design section includes, if a design section protrudes outside of the beam, for example, in this case, the design cut goes from here out to here, and then from this point out to this point, that in essence becomes a T-beam because the design cut extends beyond the flange of the beam. So in this case, I'm allowing the program to just determine the design cut, or let's say the flange distance for me by how I input the support lines. If I turn off the strips or discard them, when the program generates the tributary, it's saying it's taking the distance between these two lines, I'll call that L/2, and the distance from here to here, because this is a free edge of the slab, and that becomes the design cut. So that in essence becomes your flange width. And in this case, let's say we had a beam along this path. This would take L/2 plus maybe this is L2/2, and that becomes the flange for this beam. So to manually dictate how wide the flange is, the user has to input those splitters in the model to determine, how wide the flange is. So let's say for this beam along this path, just assume there's a beam there, I want the program to have only 5 feet on either side. I would have to add a splitter, and I would take a splitter, and maybe this is 5 feet. I would have to add a splitter on either side of this beam in order to dictate a 10-foot flange for that particular beam. And that's going to change, by the way. We're going to introduce in 2018, hopefully, a beam manager which allows the user to modify the flange width more easily versus actually graphically having to modify it, where you can enter values for the flange width and the program designs based on that beam manager input versus the graphical input. Question. Do we plan on doing webinars for PT slabs? Yeah, we're trying to do several webinars a month. I do a lot of the webinars, and then our sales staff does some of the webinars, but I can definitely plan on doing a PT design seminar in the near future. So that's the topic we could cover next month, or actually in August, later on this month potentially. The question is, did the beam torsion stiffness take into account in the analysis of the slab? Yes, the torsional stiffness of the beam is considered. If you want to basically ignore it or turn off the torsional stiffness of the beam, we have the ability to do that by means of a stiffness modifier, but the more direct way would be under criteria, analysis, and design options. You can go down here and basically ignore the torsional stiffness of beams. That's a checkbox here, or you can reduce it per percentage in this input field here. And the program, one thing to mention, it does not design for torsion. It reports torsion, it calculates torsion for beams, it doesn't design for torsion. I had a question today from a client, why not? The simple answer is we just simply haven't programmed that in our designer up to this point. It is on our roadmap for development, but the program reports the torsion, but it doesn't design for beam torsion. It will design for twisting moments in slabs and two-way slabs if you use the wood armor option, which is shown right here. This includes design of twisting moments per the wood armor method. Shear in beams, yeah, the program does design for shear in beams. So take this up here, for example, this design strip. If I go ahead and generate that design strip again, and I design this one particular strip, whenever you have a beam design section, the program will design for one-way shear. So there's 3 different ways to view the results. The first way is in tabular format. If I go to reports, single default tabular reports under design section data, and I look at the rebar for my design sections, and I'll do this just for strength, for example. Each one of these design cuts has a unique ID, and the tabular report is formatted to map to those IDs. So you can see this for support line number 1, I have multiple design sections. This is span number 4, I think. So we have span 1, 2, 3, 4. So this is span 3 along this beam. And going back to the report, if I look at span 3, which is this block, you can see I have both longitudinal reinforcing that's output, which are these cells here, but I also have shear reinforcing. So it's 0.24 inches squared per foot at 8-inch spacing, for example. And what's the bar size? Well, the bar size is defined in the criteria under shear design. So for one-way shear, I'm using 2 legs, and the bar size is a number 5 stirrup. So the tabular output gives you the area per foot or per meter and the spacing. You can also double click on this strip and choose to generate the design cut or the elevation view, and that actually shows you the outlay of the stirrups right here, along with it should also show longitudinal rebar, but I haven't generated the design drawing, the rebar drawing. That's why it's not shown here. The third option is if you double click on the strip and go to the builder sum file, this would also output the shear stirrups for the beam here. there was another question here. Let me go back to that question about, okay, there was a comment that someone's screen did not look like mine. For criteria, I don't know. I'm sorry, I'd have to see your screen. It could be that you're in adapt PT mode when you launch the program. There's RC design scope and then RC and PT, and depending on what is selected, that defines what is populated in the criteria input fields. So that could be the reason. Okay, I appreciate everyone's help. We'll go ahead and conclude there, and I appreciate your time. So again, if you have questions, please let us know. You can email us, and we'd be happy to give you a hand. Thanks again. Have a great day.